Mr. McLeod here. I been asked recently to try and make sure that I start putting some of our work on YouTube. And the reason is some students are using things like Khan Academy or other websites. What they're starting to find is that, well, it isn't really helping them solve the most complex of problems that we're getting. So what I'm going to do right now is I'm going to work you through one of the hardest problems we're going to go over. And you can use this as sort of your Rosetta Stone or key to solving all your other problems. Now, the problem we're going to be working on today is problem 19. You can see it right here. We have a picture. I kind of drew on it in pen, but man's kicking a ball. It lands on a roof. Yeah, he's some distance away and he's some height. Okay, I'm going to read the rest of the problem. A playground is on the flat roof of a city school. That sounds totally dangerous. 6 meters above the street below. The vertical wall of the building is 7 feet. Okay, high, to form a 1 meter high railing around the playground. So 6 foot wall, let's try that really quickly. We have a 6 foot wall right here. Sorry, 6 meter wall, right? And it's a little bit higher because there's a 1 meter fence. So we're just going to go ahead and write the total height. I'm going to guess already that they're just trying to throw us off by adding in the idea that there's 2 heights. Okay, and like I said, we're kicking a ball from somewhere over here. Let's keep reading. The vertical wall of the building is 7 meters high to form a 1 meter high railing. A ball has fallen to the street below, and a passerby returns it by launching it at an angle of 53 degrees. Man, this is a brave man. So let's see. He comes over, Billy Bob here, whatever we want to call him. He decides to kick a ball, and the ball goes flying at an angle of 53 degrees. So, I see degrees. My first instinct is, at some point we're going to be doing some vector components. We're going to be breaking this apart into an X and a Y, and that's going to tell us basically what gravity's doing and how far this thing's going to sail. And you'll come to recognize this the more of these sort of problems that you do. Alright, let's continue. 53 degrees. Our distance to the wall is 24 meters. And, what's the last piece of information we have? It takes the ball 2.2 seconds. So we got a time. That is really important. So I'm going to keep our time, write our time in pink. T equals 2.2 seconds. Now, what does it say? The ball takes 2.2 seconds to reach a point vertically above the wall. So, once again, a point vertically above the wall, that sort of tells me that that's going to be this point right here. That's going to be this height. This is going to be our absolute highest point in the arc. Okay, you're going to get these problems often in physics where you come to the thing and you're going to think, okay, what is the turnaround point? Well, we know the time to it, and that's really powerful. Okay, we're going to use this information to solve the following questions. A, find the speed at which the ball was launched. We'll just start with that one. The speed with the ball is launched. Okay, well, I have an angle, I have a distance, I have a time. Having distances and time usually means we can find a speed. Okay, well, let's see what I did here. Well, I decided it was easiest to go for a horizontal speed, and then use my horizontal speed to sort of reverse engineer this one. And you'll see what I mean here in a second. So, well, I know it took 2.2 seconds to come here. Well, that means the same thing as, or that goes along with this 24 meters, right? So we know we went 24 meters in 2.2 seconds. So, just in the horizontal, right? So in the X, so I'm going to say velocity, in the X direction, okay, has to equal, well, distance divided by time. Remember our base equations, write it over here. V of X equals distance over time, or if we want to be more correct, it would be that X final minus X initial over time. It'll be sort of that total displacement, total distance. Well, our distance is 24. They already gave it to us. We don't even need to worry about the start and the end points because we got the whole shebang. 24 meters, and we're going to divide that by the time, 2.2. Okay, and that's in seconds, of course. Oh, what do we get? Okay, let's zoom in on our calculator here. I'm going to get 24, just to make sure I don't make any mistakes. 2 equals, and we get 10.9. Let's say 10.91 about. So I'm going to say approximately, or this is the symbol for approximately, 10.91 meters per second. Now remember, it is absolutely important you remember that this is just our horizontal distance. It's how long it took us, it's how fast we are going to go this distance in this time, and that's just here. The distance going up is obviously going to be a little bit different. That's going to change what we get. Now we're going to use this number to figure out this number. What we're going to do is we're going to use a little trigonometry trick here. And so I'm going to, since this is v of x, I'm going to put it on in sort of an imaginary x-axis. So that our x-axis is 10.91, and we don't know what the y is yet. We'll figure that out later, so let's write a y here. But what we're looking for is we're figuring out what the total is, what the combined y and x. So remember from vectors, if we can figure out this one and figure out this one, we can figure out this one. Well, today we're not going to figure out this one, not until the end of the problem almost. We're only looking, I'm going to call this r, we're only looking for this one. And fortunately, we have an angle. The nice thing about this trig function is, to figure out another side, all you need is either 2 sides or one angle and one side. So to do this, I'm going to use the trig function that uses this side and completely pretend that one doesn't exist right now. And we know that is, this is the adjacent angle to that, and this is the hypotenuse. Well, adjacent over hypotenuse is cosine. Remember, SOHCAHTOA. So the cosine of 53 degrees equals, okay, adjacent over hypotenuse, 10.91 over r, 0.91 over r, and we're going to have to rearrange a little bit because we're trying to find r, right? So rearranging this, we're going to get 10 points. I'll just draw a little arrow down. My whiteboard's a little low here, so we have to crouch down a little bit. We're going to get 10.91 divided by that cosine of 53 degrees, and that'll give us our velocity. Remember, this is meters per second. That's going to give us our velocity in this diagonal, or actually our total velocity. Okay, so let's do that really quick. Just here on the calculator. 10.91 divided by, I'm going to put a bracket in there, cosine, I guess I didn't really need the bracket, but we'll do it anyway. 53, close brackets, and we get a speed of 18.12, or 13. We'll say 18.13. I think the book has 18.1 in this situation. Okay, because this is actually a solution, I'll write it in pink. I'm going to put a little cloud around it. 18.1, and like I said, this is a cloud. This is meters per second. Keep in mind, this is our total speed of where this went. This isn't the y or the x, this is the combined one. Okay, cool. So we're partway there. Okay, small whiteboard. We're going to see if we can make this work still, though. Okay, part B. Find the vertical distance by which the ball clears the wall. Okay, so we want to know, we know that this thing has to go at least 7 meters to clear the wall. We have, well, what I'm thinking now is, because we're looking for a vertical distance, there's only one formula that I usually think of when it comes to turn to that, and it's the kinematic equation that uses, well, the vertical distance. And that is, I'm going to clean this up a little bit. We know where most of this came from. So let's get rid of some of the things that we're not going to need anymore. We already figured out v of x, and I'm going to leave that there, but I'm not going to get rid of that because I want some room to work. Alright, so like I said, we need to find our vertical distance. The equation for that is y final equals y initial, so our starting point, plus our velocity in the y direction, remember I told you we were going to get that eventually, times time, plus 1/2 g t squared. Now, usually you'll see this as a/t squared acceleration, but we know that a is gravity because all of our acceleration in the y direction is just due to gravity today. Alright, so that's what we're going to do. Let's get rid of some things. What's our starting point? Well, we're starting at a y of 0, so we don't even need to worry about that. So that becomes 0 let's just get rid of it. Okay, velocity in the y. Well, we figured out our velocity in the x. Let me put that back there for you. And we figured out our total velocity. Well, we're just going to do the same thing we did to find those ones to figure out that missing value. So v of y, let me start over here so we got plenty of room. V of y is going to equal, well, look at our triangle here. We could do, if we wanted to, we could do opposite over hypotenuse. That'd be sine. Yeah, let's do that. And we know that r, I'll just write it up here, equaled 18.1. We already figured that one out. So we're going to say sine of our angle 53. And remember, sine literally means how much y, how much up and down we are. Just like cosine meant how much left and right we are in our vector. So sine of 53, let's make that a little neater, huh? 53, I'm running when you're down this low. Sine of 53 is equal to, okay, well, it equals to opposite over hypotenuse. So it equals y over 18.1. And once again, we need to get y by itself because we just want to know what our y velocity is for this situation up here. So rearrange, that just becomes y equals sine of 53 times 18.1, right? Because we multiply both sides by 18.1, it just comes right over 18.1. Okay, let's look at our calculator one more time. We're going to go sine 53. We're going to multiply times 18.1. I think we get 14. Yep, 14.46, we'll say. So our final answer on that one is going to be v of y is approximately 14.46 meters per second. Now remember, this is not the solution for part B. This is just the part way there, right? So now that we have a number there, we know this. I'll put checks above what we know so far to make this easier. We know v and the y. We just figured that out using this whole equation here. We know time. Time's still 2.2. It's the same point. We're just worried about up and down now versus left and right. And I know g and I know t. So there's nothing on here I don't know. Remember, the t was the same, 2.2. So we know 2.2. G, 9.81 meters per second squared, because we're on Earth, and t is 2.2. So let's just plug in some numbers here. Okay, so simplified, v of y, 14.46, times t, which is 2.2, plus 1/2. Let's just say 0.5. It's the same thing as 1/2, but easier on the calculator. 0.5 times 9.81 times, well, same thing, that 2.2, but this time we're squaring it because this is our acceleration squared. I don't want to run into our picture there, but that's the whole thing. Let's see if we can just put that all into the calculator here. We're going to go 14.46 times 2.2, okay, plus 0.5 times 9.81, close the bracket, times 2.2 squared. Now, it's really easy to make mistakes like this. Sometimes when you're doing this, you need to go step by step by step and write down each part of the problem. But I'm pretty confident we got it all in there. Let's see. Okay, so I got a y final. Okay, now I know this is wrong. So I did something wrong here. Let's go back one more time. Let's try this one more time. Okay, we've got our y velocity times time. I probably did a 22 instead of a 2.2. 14.46 times 2.2 plus, I'll put a bracket here just in case, 0.5 times 9.81 times bracket 2.2 squared gives us 55.55. Okay, I'm doing something wrong here for our y distance. Okay, let's look real fast. We got our initial velocity. We got our time. See, even when I get at practice, we make mistakes sometimes. Initial velocity, got our time, got our velocity, plugged it in. Okay. Well, let's just do it step by step. I'm probably just making an algebraic mistake here. All right, 14.46 times 2.2 Okay, that gives me 31.812. Oh, I made this mistake right at the beginning. Fundamental physics mistake. Hey guys, which way does gravity point? Down. So what happens when gravity points down and our velocity's up? I gotta make gravity negative. Very rookie mistake. My bad. Let's try that one more time, alright? 14.46 times 2.2, cool, plus, bracket it, 0.5 times 9.81 times 2.2 squared gives us, yeah, I did it again, didn't I? Minus 8.07. That looks better. Okay, that was done right that time. Okay, so basically all I kept doing was I kept saying the 9.81 was positive. Got to remember our vectors, right? Gravity's negative if everything going up is positive. Got to remember that. Okay, so let's get rid of all the fundamental work I did here, as long as everyone's seen it. Okay, and I can get rid of this equation, and we know that the answer for B is that y final is equal to 8.07. That's the same thing as saying our height, right? Our height above here. Now that the real question is how much higher above this are we? Well, 8.07 minus 7, our height, I'll just put an H for that, our total height above the 7-meter fence and wall ends up being 1.07. Cool. And I'll put a little clad around that like I did with the other answer. Remember, this was answer to A. Okay, we have one more question. We have question C. C says, find the horizontal distance from the wall to the point on the roof where the ball lands. So here we go. We got the wall right here. We know that's where we're starting. We want to know where it's going to land over here. This is actually really simple. It's easy to complicate this and try to figure out, okay, well, we need to use this whole piece of information. All we're doing is saying, hey, our starting point is no longer 0. Our y initial is now this, that 1.07. We're starting here. We're going to pretend none of this happened before. We're just going to use this trajectory to figure out this distance right here. If we can figure that out, all we got to do is add it to the distance we already have, and we'll have the total distance traveled. But I think the question doesn't ask for that. I think the question just asks for this piece right here, right? How much further did we go beyond that? Well, let's erase a few things because we have plenty of room. Okay, so I'll leave up our solutions. And I'm going to get rid of some of the work that we did up until now that we don't need quite so much anymore. All right, there we go. Now, there's a couple important things about our starting point up here, but we'll talk about that as we go. So I'm going to work in the bottom left-hand corner here. And, all right, starting up here. Well, I know because I'm trying to figure out horizontal distance. But before I can figure out horizontal distance, I kind of need to figure out how long it takes. Because my horizontal equation is x equals velocity times time. Well, we know the velocity in the x. It hasn't changed. Remember, there's no acceleration in the x direction ever. Unless we're dealing with air, we're not doing that in most physics problems. We're not dealing with air. So there's no acceleration here. All of it's here. So this number has not changed along the whole path. It stayed 10.91. So we know velocity. Well, the only thing we're missing is time. And of course, we know time up to here, but we have no idea how long it took to do this part. If we can find time, we just need to plug it in here. So the only way I know to find time that easily is to go back to our y equation. Our y, our distance, velocity, time, acceleration equation. Okay, it's the one that has everything in it, right? All right, so our y final, right, is some distance beyond there. Sorry, no, our y final is here. We're going to pretend our y final is 0 because, like I said, all we care about is there. This is pretty much a whole new problem. We're going from here to here. Our y, our up and down, this is going to be 0. Cool. So y final just became 0 equals y initial plus vt, remember that's v in the y, velocity in the y, plus 1/2 gt squared. And I'm going to be smart this time. I'm going to make this minus right off the bat because we know that our g is going to be negative, right? And we don't make the same mistake I did last time. Okay, y initial. Where are we starting? How high above our new zero, our new imaginary starting point are we? Well, we solved that before. We're 1.07 meters, an m there. We're 1.07 meters above where we started. So I'll plug that in there, 1.07. We're going to add that to our starting velocity. Now this is where things get tricky. As we're coming up, we had a starting velocity of, well, combined velocity of 18.1, but a y velocity of 14.46. But if you think about it, right when we hit the crest, right at that new point that we're saying is our new starting point, our y velocity was 0, right? Because we're not going up anymore, and we're not going down. Just at that exact moment that we started, we are going 0 meters per second up and down. So because of that, because we have a starting of 0 just in the y. Remember, we still have x the whole time. We have lots of velocity in the x. But because we have nothing in the y, in our y specific equation, we can say now, hey, you know what? Y 0, this is starting, the starting velocity is 0. Well, because that's 0, that just disappears. We don't need it now because anything times 0 is 0, right? And all we're keeping in here, in fact, is minus 1/2. Now remember, g is gravity, 9.81, 1 t squared. And remember, that equals 0. Okay, well, let's move everything over there. We're going to get negative 1.07. And we want to bring the 1/2 over to that side as well, so we're going to multiply that by 2, and we're going to divide by 9.81, and then we're going to undo the square here by square rooting this side, and so to get to the point where we're equaling t, that's what it looks like. So let's solve that question real quick. So on the calculator, we're going to go square root of 2 times negative 1.07. Simple. Oh, by the way, gravity was negative too, right? So let's keep that negative. Okay. At the end, this is all going to become positive, right? Negative divided by negative. But I'll keep everything straight in here, like I'm supposed to. Okay. Divided by negative 9.81. And we want to make sure we close all those brackets, right? And that becomes syntax error. Let's try that again. Why did it become a syntax error? Okay. 2 times negative 1.07 divided by negative 9.81. You know what it is? I just used one too many brackets. And we get 0.467 seconds, right? So time equals 0.467 seconds. Okay, so we have a time. Now remember what I said. This is what we're looking for. This is not what we're looking for. We can use this time. Now we know how long it takes to hit the ground. The beauty of this is the same amount of time it takes to hit the ground coming down is the same amount of time as it's going forward. It's the same time. So what we're going to do is we're going to take this number, fish it up here, bring it over here, and plug it into our base equation. So we have a time, 4.67. Let's make some room for it. We can do our little calculations here. Now, I will admit, this problem does have a lot more parts than your typical physics problem. Okay, there's lots of steps involved. Easy to make mistakes. Like I said, easy to not misplace a negative. So t is 0.467 seconds. Okay, and remember that's s. I'll just draw a little s because my handwriting's so bad. And our initial velocity in the x was 10.91. 10.91, and let's just multiply this by 10.91 then. Do the same thing we're doing up there. And we'll get 5.09 meters. Okay, so that means we're a little more than 5 meters beyond the edge of the wall. So if we were to actually get a total, that means this guy kicked that ball and it flew 29 meters. Okay, now think 29 meters, well, let's multiply that by 3.25. That's about 94 feet. That's a pretty decent kick. I hope no kids were standing there when that ball came down, because that's probably moving pretty quickly at this rate. Anyway, I think we did a great job here. That's physics. I'll talk to you guys later.